So hello everyone, this is my update for February 17th. So the major focus I'll have for this presentation is on a new fused matmul compression kernel. So to give some context on our mixed sparsity algorithm, imagine we have a sparse matrix here. We are going to split this into tiles of sparse and dense tiles. And for the sparse tiles, we follow a structure 2-4 sparsity, which I'll be discussing later. But we split this into tiles. In this case, it's 4x4 tiles. And we follow a compressed sparse row format. So the sparse tiles is ordered into a row as well as the dense tiles. And how we do computation is we iterate over each tile in the sparse row. We compute a dot product, and then we do the same for the dense product. So the motivation behind this new kernel is that currently we have pruning and compressing sparse matrix, and this happens outside of Triton. So what that means is when we do a matrix multiplication, we have to store it back into memory, call an external function to prune and compress our results. And then the next time we want to use this sparse results, we need to load it again. So our goal is to perform this pruning and compression process directly in register, so directly within the Triton kernel. So by doing so, we hope to reduce memory traffic and also improve performance. So just to illustrate what I mean, this is a typical workflow of, so the above is what we currently have and below is what we want to get to. So they both start with loading the two matrices. One of them is sparse and one of them is dense. In our kernel, we want to perform matrix modification. But in our current workflow, we have to store the results back into shared memory. And then we call a function to prune and compress the outputs. And then later, when we have other operations, we would load this sparse outputs. What we want to do now is instead of sorting this back into memory and rely on an external function, we want to have this in Triton to do this in the registers. So after we finish our matmul, we can directly prune and compress our outputs in the registers. And after that, we can either store the results back into memory, or we can perform the next operations directly. And this has a few benefits. So for example, after a matrix multiplication, we might want to have some kind of activations that happens. And activations can make the results more sparse. And so after the activation, we would want to directly convert that into our sparse format so that it can be used directly for the next operation in training or in inference. So I just want to spend a bit of time talking about how we are currently compressing our values for a sparse matrix. So we use the structured 2-4 sparsity, which means every two elements of every 4 elements in a row are zeros. So you can see here that we grouped into groups of 4, and 2 of them are zeros. So in this case, 1 and 2 are not zeros, but the other 2 values are zeros. And we split the sparse matrix into values and metadata. So this is an example of how we can take a sparse matrix, we convert that, we keep the values, and we also have the metadata that indicates where in the group of 4 these 2 values belongs to. So just to recap, the indexing, we need 2 bits to store the index of each non-zero value within the 4-element group. So these values are going to be between 0 to 3, right? So 1 here corresponds to the 0th value in the group of 4, and then 2 here corresponds to the second value in the group of 4, and that converts into 0 and 2 here. For a 16x16 MMA tile, we store the metadata as a 16x1 in 16 tile. So as you can see here, this is what the metadata looks like. We have, because there are 16 rows, that corresponds to 16 rows of metadata here. And because there's 16 elements in the MMA tile, we're going to have 2 bytes. So essentially each bit or each element in the tile corresponds to 1 bit in our metadata in the row. And so in order to maximize efficiency, we have some intra-tile reordering as well as some global reordering. So to give some context, the sparse tensor course requires 8 threads per warp to supply metadata for a single MMA operation. So imagine we have the metadata like this. We have 8 threads to fetch this metadata. And what would happen is each thread has to issue 2 load instructions because one of them, so the first instruction is going to load, for example, the 0th row, and the next instruction is going to load the 8th row. And this is for one thread, and we want to maximize this. So because each load can load 32 bits of data, it's better for us to reorder it into this tensor on the right side here, so that there's 32 bits across a row, and it's contiguous in memory. So imagine we have 8 threads now that's trying to fetch the metadata. Each of them can just issue one load instruction and fetch the entire row of 4 bytes, and not having to issue 2 instructions. And on a global scale, we also have reordering as well to maximize memory efficiency. So a warp has 32 threads. And like I mentioned before, the tensor core requires 8 threads to load data for one MMA operation. So because there are 32 threads, we can actually load metadata for 4 consecutive MMA tiles. So each one of the 8 threads is going to load data for one MMA tile. So what we do is, this is kind of what the MMA tiles are laid out in memory originally. And we reorder this into a contiguous 128 bytes in memory. So that each warp, each group of 8 threads is going to load the data for one MMA tile. So we also lay it out in this kind of coalesced fashion, so that one LD matrix is going to be able to load this entire 128 bytes of data. And this will be enough data to perform 4 MMA operations at once. So here is on a high level what the kernel implementation looks like. So above here we have a normal sequential kernel that we have to compute a matrix multiply results. So I'm not going to walk through this because this is identical to what we have before. So the difference is down here. After we get the results from the matrix multiply product, we're going to split this into groups of 4, and based on that, we're going to get each element in the groups of 4, and we're going to call this prune and compress function. That's going to look at the 4 elements in each group and only keep the top 2 elements in the group, so the 2 largest elements in the group. And it's going to store the sparse values and the sparse metadata into the correct corresponding address in memory. So for testing to verify our kernel is working, I compare results against the original workflow to make sure it's matching what we're expecting. And I also verify the correctness across different matrix sizes as well as different configurations for the kernel. So there's currently some limitation, and the biggest limitation is we require the second dimension. So in this case, this will be the batch size to have greater than 64 elements for efficient usage of LD matrix. And the test also currently uses n equals 64, and it's different from the usual 16 elements for the batch size. So we have this limitation because we wanted to fully utilize the LD matrix operation, and we wanted to load 4 MMA tiles at once. If we only have 16 elements in a row, then we won't be able to efficiently utilize the LD matrix operation. So here is some results for benchmarking on the A6000. So it's showing, as you can see here, the graph here, the blue bar is the sequential kernel. This means that there's no, it just performs as the matrix multiplication. There's no pruning and there's no compression. So this is our baseline. The orange bar is our fused kernel that we implemented that does the pruning and compressing within registers. So you can see here there is a little bit lost in performance. But overall, if we compare this to the reference, which is the green bar here, we can see that the fused kernel actually is performing much better than our reference implementation, which requires us to store the data back into memory and use the external PyTorch function to do the prune and compress. So overall, we see that by doing our pruning and compressing the registers, there's very, very little loss in performance. So in terms of next steps, I want to do a bit more extensive benchmarking. So that means different matrix sizes, more configurations, and also on different GPUs. We also want to apply this to other use cases. So for example, we might want to see what the performance is like if we add in some kind of activation function, and then do the pruning afterwards. We can also see if we can kind of combine two matrix multiplications into one kernel. So whether we can do one matrix multiplication, prune and compress it, and then immediately use the results in the next matrix multiplication without ever having to store these data into memory. So that'll be something that we're going to look into in the next steps. So thank you so much for listening to my presentation. And have a good day.